Yesterday we crashed Adobe, by the looks of things. Yep. Sorry, technical fault in an engineering department. Who'd have thunk it? Anyway, yesterday we were looking at transistor characteristics. There we go. Somewhere in this lecture is a nice big image, and the poor old computer is struggling with the idea of transferring it between the pages. Anyway, yesterday we were discussing transistor characteristics, and we looked briefly at numbering systems for devices, that's to say the JEDEC and the pro-electron system, and then we considered 4 modes of operation for a bipolar transistor, and I drew a little, not really a graph, but a kind of a graph, which showed the 4 modes sort of next to each other in terms of the collector base junction voltage and the base emitter junction voltage. And then we looked at some examples of input, output and transfer characteristics for the bipolar transistor. And I talked for a bit about the sort of graphs that you might find on a data sheet. And then I spent most of the second half of the lecture talking about large signal model, or working towards one anyway. And we had a large signal model for a bipolar transistor under all situations. And then we developed that a bit further into a bipolar transistor which is switched on, and we said there are 2 saturation voltages, base emitter saturation voltage and the collector emitter saturation voltage. And the situation for the transistor switched on is both junctions forward biased, so the base is the highest potential electrode in the system, and the collector and emitter are quite close together. And we went on from there and said we could have a model, a large signal model for a transistor that's switched off, and that's 2 open circuits with no diodes switched on at all. And then I talked for a bit about MOSFETs, and we very, very briefly, because I was running out of time a bit, had a model for a MOSFET, and we said, unlike the bipolar transistor, there is no gate current, because the gate is insulated from the rest of the device. So we could have an open circuit, and I did say that there was a capacitance that had to be charged up, but in this course we would ignore it. And then we had a large signal model for a MOSFET that was switched off, and that was also no connections between any of the electrodes. And I said today we talk about switching circuits sort of for the first time, and we do some preliminary examples. And in the lecture that follows this, we'll do some examples that you might find on a tutorial sheet. Problem sheet. It's a problem sheet. To that end, the problem sheet is now in circulation. So if you haven't got a copy of the lecture notes and a copy of the problem sheet, then you're missing something. Let's have another go. Right, so this is today's lecture. We've just done the review. Then I'm going to talk about switches, as in mechanical things that you flick with your finger. And then we're going to talk about the switch types sort of in more detail, and we'll say the differences between mechanical, electromechanical and electronic switches. And then we'll talk about the MOSFET and the bipolar transistor when we want to use them as a switch. And we'll discuss some characteristics of the transistors. It's alright, they're assassins, it's fine. We'll discuss some characteristics of the transistor which make it imperfect, and we'll talk about power dissipation, and we'll give some specific examples towards the end. So on the next slide, which it will pull it up eventually, I've got a real switch, in quotes, which is an ideal switch, so what you would think of as 2 pieces of metal that contact each other. And in series with that is a resistance, and this resistance represents the complete distributed resistance of all the fact that the copper has a certain resistance per unit meter, and that depends on its cross-section, its thickness and so forth. All of that resistance is lumped into RS. So RS represents the loss that will occur in this switch when the switch is open, when the switch is closed. Where have you come from? What was the prior lecture? Next door. Do you need a map? Right, so there's a tutorial sheet and some notes, so don't forget to take both. Then we have a parallel resistance, and this is the resistance that dissipates power even when the switch is switched off. So in a real mechanical switch, there is almost no current flow between the two electrodes because there's a really big air gap, and air has an enormous resistance unless it's broken down. And to break down air, you need about 1,000 volts for every millimetre you want to break down at sea level at a reasonable humidity. So for a sort of 5 or 10 volt circuits, it's very, very difficult to make an arc. So RP is practically infinite, RS practically zero, and that's the situation for the ideal switch. But as I've said, the switches we'll be looking at aren't ideal, and we have to worry about what RS and RP might be. So to work out the current in the switch, we'll say V supply, which I've abbreviated to VS on the diagram, divided by RL plus RS. Now, RL isn't on the diagram, which may be a bit of a cheat, but RL is the load that we want to change the current flowing through, so it's connected in series with the switch. And from this point on, RL will usually appear. Right, this is the diagram that's giving me all the grief. So mechanical switches of the kind that you can buy from RS and Rapid and whatnot, and on-off is generally their purpose, or beloved available students is the missile switch, which has a lovely little red cover that you have to lift up before you can flick it, but basically it's just an affectation. So mechanical force brings together two metal contacts, and these are easily designed for currents in the range of a milliamp to about 10 megaamps. Above 10 megaamps things get very, very tricky, and below 10 milliamps, below a milliamp, sorry, after a long time the contacts tend to oxidize somewhat. And then if you unswitch, or you open switch and then you close switch again, you can find that the contact isn't nearly as good as it used to be. Similarly, when you're closing an enormous current, there will be an arc beforehand, and that arc will oxidize the switch surface, and then there will be some difficulty making the contact. Also, breaking an enormous current requires quite a big distance, and you have to do cool things like fill the switch with oil to make sure the arc is quenched. But that's really power distribution stuff, and I don't want to get into it. But a milliamp to 10 megaamps, relatively easy. So they have very, very low contact resistance and very, very low leakage. That's to say, RP is very high and RS is extremely low. But they require the application of some mechanical, that should be mechanical force, not mechanical force. Third or fourth one down, just there. There's an S and an E missing, the R needs to go away. Mechanical force to operate. They've got elasticity and inertia. That's to say, when you flick the switch, you're pushing a little ball bearing across inside, and that's sort of making an armature move down. And the armature, even though it's metal, it's quite thin usually. And what happens as you push it down, it will deform like that, and then it touches down. And that time in the deformation, the same goes for when you pull away. The current wants to keep flowing, so there'll be a little force on the point where the contact is that you're trying to break, so there'll be a deformation like that. And that elasticity, that stored energy there, and the mass of the moving part limits the rate at which you can flick the switch. Now, the other thing that breaks the limit that you can flick the switch is how fast you can move your hand. But in a relay situation, we've got something to take the place of our hand, which we'll talk about in a minute. And we still can't get much above a couple of hundred hertz. And if you do, the relay will die very quickly, usually. So the need for a mechanical force requires some kind of linkage between the switch and the operator as well. You have to be physically close. And if you've opened up any recent Agilent sort of kit, early 2000s onwards, what they're doing now is that I'm talking about like a signal generator or a power meter or something like that, benchtop bit of kit. They'll put a switch mode power supply in the back, and they'll, to meet some regulations at a lower cost, they want an on-off switch on the front panel, and their on-off switch is on the back panel next to their switch mode power supply. So what they've got is a long bit of plastic, and it's a funny shape to go around all the magnetic components and whatnot which are in the box. So there's this, the box is this big, your finger pushes there, the switch is back here, and there's a bit of plastic that goes like that to make the... It's cheap, much cheaper to make that than to wire the switch on the front and deal with all the electromagnetics that are involved in making sure the design still works properly. So you have to have some mechanical force, and that doesn't necessarily mean the length of your finger. It can be a bit more complicated than that. So, similar to mechanical switches, are electromechanical switches, except that the mechanical force is now provided by an electromagnet. So this we will call from now on a relay, because that's what everybody calls them. And that is derived from when they were used for telephone applications. So an electromagnetic drive scheme offers the possibility of remote operation. That's to say, I'll pass a current through an electromagnet, a magnetic field will be generated, and I will pull some soft iron part towards it, and the switch will be connected by some linkage to the soft iron part, and it will move accordingly. So the advantage of mechanical contacts are maintained. That's to say, the off-state loss is extremely low, practically nil, and the fact that you have total isolation between your circuit that is driving your relay and the circuit which your relay is switching is also very useful, and that's one of the main difficulties of transistor is you've only got 3 electrodes, but what you'd like is a controlling parameter, which is voltage, so it's got a positive and negative, and you've got a control parameter, which is probably going to be a voltage, so you've got a positive and a negative. So really, you want 2 positives and 2 negatives. But with a transistor, you've only got 3 electrodes. So one of those electrodes must be shared between your driving circuit and your driven circuit. And we'll come on to that in a minute. But most toggle switches, so these are on-off switches, are rated for about 10 raised to the 5 mechanical operations. So after about 100,000 switches, you can expect, on average, that it'll die. On the other hand, they can manage 10 to the 6 electrical operations. But that's neither here nor there, because after 100,000 switches, it's going to die anyway. And it also depends on the application. So if you were in some, I don't know, electric car situation, and you had a big battery pack in the boot of your car or whatever, and you were using it to drive some hybrid powertrain, and something went wrong, and your safety systems, your ECU, decided to cut the relay between the battery pack and the drivetrain, and it was at full tilt, you'd only get, and you use this relay that I've given the part on for you, so you can look up its specs if you want to. You'd only get 25 cuts, and then the relay is dead, because breaking that current oxidises the terminals and upsets the relay. Breaking no current is very easy, it's just moving 2 pieces of metal. So not only is it dependent on the mechanical wear and tear, it depends on the electrical conditions when you're making and breaking the current. So oftentimes in this sort of situation, we have some power semiconductors to decide when the current's on and off, and the relay will be our last line of defence. So we relay down, power semiconductors do switching, relay passes current without any arcing or any funny business. Then power semiconductors switch off the current, and we open the relay under no current conditions, and then it ends up with a very long life. So you can use the two together to optimise the properties of both. So electronic switches, there are many different types. We will be limiting ourselves here to MOSFETs and bipolar transistors, but you may as well know about some others, bipolars, MOSFETs, JFETs, thermionic valves, triacs, thyristors, I think I missed diacs, and solid-state relays. Solid-state relays are really just a couple of MOSFETs in a big box, and they have all the properties of an electromechanical relay, but without any of the mechanical deficiencies. On the other hand, they do have quite high losses compared to just a single MOSFET, and they are not optimal for many situations. Generally speaking, they don't find very much use outside of sort of control applications. So electronic switches can change state very quickly compared to mechanical switches, and we can expect 10 to the 9 operations per second for a CMOS transistor in a modern PC. So if you've only got 10 to the 5 operations from your switch, it's all going to be over in about a millisecond. So that really illustrates the key difference. Losses in electrical switches are considerably greater, and we will be using the saturation voltage and the RDS-on, which I discussed yesterday, to work out what those losses will be. And as I said just now, the control input is electrically connected to the main current path. That's to say, your input voltage and your output voltage, or voltage and current network, both have to share the emitter or the source, usually. Most electronic switches support current flow in one direction as well, and that can be quite difficult, and we'll have to use some circuit tricks to escape from the problem when we want to have current flow in both directions. On the other hand, that's not true for the solid-state relay, but as I already said, it's a compound device, so it's cheating. So for a MOSFET and a BJT switch, this is our sort of very high-level schematic where the transistor is just a box. And the control input is VI, and the controlled variable is I switch. The control variable is not V switched. We are in charge of the current. Charge. I liked it. We are in control of the current, and the voltage across the switch will do whatever it has to keep up with our demands. Assuming we've designed it properly, otherwise it will do whatever it likes and we'll be scratching our heads. So the device is placed into the circuit on the right of the slide, and VS is the supply voltage and VI is the control voltage, and V switch is the voltage across the switch, and V switch and I switch are related by Vs minus VSW upon RL. So all I've really done there is applied Ohm's law across RL, because Vs is the potential at the upper end of RL, and V switch is the potential at the lower end of RL, and RL is the resistance of RL, so volts over ohms is amps. There is also a second relationship between V switch and I switch, which is defined by the output characteristics of the transistor, and that's why we had to do all that stuff yesterday about characteristics, which can be very confusing when you view it in isolation, but with regard to this, it does actually follow on reasonably well. So we have to move across the characteristics. Now, if I had a graph of volts and amps, and I had a resistor, I could plot on that graph of volts and amps a line which would represent that resistor, because Ohm's law says that the line will be straight, and we have R is related to V is related to I by a factor R. So the slope of the line, in fact it's actually 1 over the slope of the line, gives us what R is, and this is the R that we already know about because it's RL. So we can only go where the characteristics will let us. We can't just pick a point. Now we can go anywhere, sort of up there and that way. You don't have to stick to the lines I've drawn. There are lines all up the graph, as infinitely close as you wish to draw them. But what you can't do is move towards A from B. Now we'd really like to be at point C and point A. Point A is a situation where a large current flows through our switch, and its collector to emitter voltage is 0. So that's switch switched on, no voltage across the switch, lots of current through the switch. And we'd like to be at point C as well, sometime later when the switch is switched off, which is large voltage across the switch, no current through the switch. Now if there's no current through the switch, go back to the circuit diagram, there's no current through the load either. So this is our switch switched off situation. Unfortunately, we can't get from B to A because the transistor won't operate there, because of the way that's how transistors are. So we will always have some on-state losses. And if you were to measure between the axis and the B along this way, that would be our VCE sat. So this is I switch is Vs minus V switch upon RL, plotted on the output characteristics from the prior lecture. So the switch is controlled by VI, which is equal to VBE. We go back up there. If you imagine, actually I've got a better graph than that, a better circuit diagram than that. There. So this is ignoring RB for a bit. We'll come on to it shortly. VBE is basically equal to VI, is what I'm saying. And point C is the off state, and point B is the on state, or it's the real on state, and point A is the ideal on state, which we can never achieve. And as VI is increased, IC will increase and VC will decrease. So that's to say we will travel as the transistor turns on from the off state to the on state. This dot will move up the line. It can't leave the line and it can never get past point B. The only way you can make it leave the line is to pick a different load resistor, and then you'll get a differently sloped line, and then you'll traverse two different points. But one of them will still be on this axis, and one of them will still be up against this point where all the curves meet. So the dots on the diagram can be thought of as different operating points, but they are not quiescent conditions in the sense of AC signals, because a quiescent condition requires that you have some DC situation, and you make a small perturbation on it to give you some linear outcome. This is not a linear outcome. We are going from switched on to switched off and back again, or switched off to switched on and back again, and the changes in the device are very, very non-linear. So they are not quiescent conditions, but they are operating points. Why I'm banging on about quiescent conditions is once we're done with switches, we'll come on to amplifiers, and then we will deal with something that looks very similar, but is in fact somewhat different, and the distinction is important. I will make the distinction again at the time. So the operating point moves across a nonlinear portion of the characteristics. That is to say, it's a large signal problem, not a small signal problem. And the locus, which is the flash word for the path of the operating point across the alpha characteristics, is called the load line. And if you were to look at it in a textbook about circuits, probably chapter 1's all the stuff that everybody already seems to know when they turn up, and then chapter 2 is probably this is a transistor and here are some load lines. So you could find it in any circuit's text if you wish. And it's defined by the load resistance, that's to say its slope is, and how far up the graph it ends up is determined by how big your supply voltage is. Obviously, if I was to, if I changed my supply voltage to somewhere up here, then this line would go further up the graph. It would have the same slope. You can't adjust the slope without adjusting the resistance. Similarly, if I had my supply voltage here, I'd have a line sort of like that. So the load line is straight, and that's because of Ohm's law. And in the region between B and C, there is a very significant VI product. That's to say, volts times amps is watts. So there's a lot of power dissipation when we're going between the on and the off state. And the designer, that's you, must keep the transistor at point B or point C and must move between them as fast as possible. We will not deal with the moving between. We will just assume it happens instantly, and we won't worry about the amount of power involved. But in some other module, EEE223, formerly EEE340, obviously I thought it was too easy for 30, so that's not how it works, it doesn't work like that. So we'll have to have a little look at power dissipation. And it's my old friend and favourite comrade, the ZCX653 from lecture 10, and it can dissipate a watt and carry 2 amps. So it can control 200 watts in the load. And you can have a supply voltage of 100 volts. So I'm allowed to make VCE in the off state up to 100, but no more. So we've got 2 amps and 100 volts. So in principle, we can control 200 watts, assuming there is no losses in the transistor. So the instantaneous power halfway between B and C could be 50 watts. So if I was, this must be 0 watts because we've got 100 volts and no amps. This is 2 amps and no volts, so nothing there either. But somewhere in the middle we've got half of each, so a quarter overall. So that's how the 50 appears. But it can only handle a watt, and if you do actually put a watt through this transistor, it will get up to about 170 degrees C. So 50 watts it'll just pop and there'll be some smoke. And that's where the idea that electronics runs on smoke comes from, because when you blow it up you let the smoke out, and that's why it's broken, because the smoke has escaped. There's a lot of evidence to suggest that's not the case. The designer must ensure that the transistor switches quickly to keep the average energy in any switching cycle below the permissible limit. And there will be some more on this in some modules in the future. So from lecture 10, the MOSFET behaves like a resistance when it's on. That's to say, I said there would be some RDS on, and we can just assume that between the drain and the source, which is equivalent to the emitter and the collector, there would be some on-state resistance. And the manufacturer will specify RDS on for whatever particular current that you're interested in, or they may just give you one value if it's not varying very much with drain current. But we can work out what the drain current is. It will be Vs divided by RL plus RDS on. So we have a circuit that looks like this. Oh, silly stuff. A circuit that looks something like this. This will be our MOSFET. I'm not going to draw all the stuff in the middle because it isn't really pertinent to the discussion. And we'll have some resistor up here and some Vs, and we'll have, this is going to be ground, so this will be our VGS, which is our controlling value, and we'll have some ID here. And what we're saying is that if I do, inside here, when this is switched on, so when VGS is sufficiently large to cause a large current to flow, we're saying that all this comes down to another circuit, which is Vs and RL, and another resistor called RDS on. So now we're, that's Vs, that's 0, that's 0, 0. So really it's just two resistors as a potential divider. So all this transistor malarkey is just dressed up Ohm's law, really. So we do ID as Vs upon the sum of the two resistors. And we can say that that's in the switched on state. In the switched off state, the transistor looks like an open circuit. There's practically no current flowing. ID is 0. Vs is dropped across all of the transistor, and there is no VE voltage across the load, so there's no current in it, no power dissipating the load, no power dissipating the switch. So in the on state, the power dissipated in the switch is ID squared upon RDS on. If you don't fancy that, you can do the load voltage squared divided by, the voltage across the transistor squared divided by RDS on if you prefer. It's the same thing, but I usually go for I squared R. And this power could be significant. As a sort of rule of thumb, and it is very, very rule of thumb, 1 or 2% of your load power, you can expect, if you're not getting something in that order, you've probably done your calculation wrong. So to ensure the MOSFET is fully switched on, the data sheet should be consulted. That's because there is no sort of all-encompassing equation like there is for a bipolar transistor. So you'll have to have a look at the characteristics, that's to say output characteristics, and they will be on the data sheet. But in general, another rule of thumb, between 7 to 10 volts VGS will definitely switch most MOSFETs on. If it doesn't, you've got a very special one. And if you've got a very special one, I assume you've planned it, and therefore know what you're doing of. So 7 to 10 volts, definitely enough. Since the gate is insulated from the source and the drain, there is no current required to maintain the gate drive voltage. That's to say there is no equivalent of IB. And that's another sort of, not a reason as such, but it's another way of thinking about IB in a transistor as being something we're not keen on, as opposed to something that controls, because you could argue that IB controls IC in the transistor via HFE, but I don't like that argument. It doesn't work for me, because can't apply that to a MOSFET because there is no IG to control ID. We have to talk about VGS and ID, and for that reason I'd like to talk about bipolar transistors as having VBE and IC as well, because then we have one unified situation for all three terminal switching devices. You'll find most textbooks will be doing it the way I'm doing it as well. So the gate capacitance, that's to say in your MOSFET, everybody's happy that a MOSFET looks broadly simplest lateral MOSFET will look something like this. It's alright, it's only a little bit of semiconductor and it won't hurt, I promise. We'll have some, maybe that's going to be N+, and this is going to be N+, and this will be P+, and we'll have some, this will be glass, and then we'll have on top of that probably something, maybe nickel and gold. And this will be our gate electrode, and we'll have some contact here as well, and this will be our, now the way I've drawn this, it's basically symmetrical, so it doesn't really matter if I call this drain or source, so we'll go drain, and this one will be the source, and we'll put a voltage across here, and that will yield ultimately a current ID flowing down there. And what has to happen is minority electrons that are living in here, there are more holes than electrons. What we really want to do is using a potential on the gate electrode is to attract electrons up here until we've got enough of them in a region here that this P+ material looks in this specific bit more like N+ material because there's a high concentration of electrons. And once we've achieved that, it will be easy for current to flow from this electron-rich environment through our inversion layer into this electron-rich environment. So what we're really doing, if you like, is we're reducing the, you can't really call it reducing the resistance because, well, we are a bit, but I don't like that. What I prefer to say is that by attracting electrons, we're creating a channel through which the current will flow. If you're not keen on that, don't panic, it'll be coming back in a second year. Or you can try, come on. Right, that'll do. You can try solid-state electronic devices by Streetman and Banerjee, or the physics of semiconductor devices by SMZ, or there was a lecturer here a long time ago called John Allison, who wrote an excellent book on semiconductor physics, but it didn't have very big circulation. I think he passed away just before Christmas, actually. Anyway, so where I was getting to with that, which I never actually said specifically, is we have a large electrode here, which is made of metal, and we have a sort of not very semi-insulating bit underneath, because this is full of free carriers. Most of them are holes, but there are some minority electrons as well. So what we've really got is something which is conducting, a piece of gold, something which is insulating, a piece of glass, and below it something which is broadly conducting. So we've got conductor, insulator, conductor, which is a capacitor. So this is how the gate capacitance comes into being. And if you want to put a voltage between there and there, you have to put enough charge on that gate to charge up that capacitance. And that's how the that's how I did it that time. That's how the gate capacitance comes into being. And in later modules, you'll worry about how long it takes to charge up that gate capacitance, because when you're charging up the gate capacitance, you'll turn the device on, and that process takes some time. So in that time, you'll dissipate some power, and that power dissipated in that switching event is called the switching losses. And they are usually much more significant than the on-state losses. But we won't deal with switching losses here. That's purely for your interest and amusement. Moving back to bipolars for a bit. When a bipolar transistor is fully on, that's to say at point B in our graph, this graph, that graph there. So we're at point B in our bipolar transistor. voltage dropped across it is VCE sat, and we get that from the data sheet as I said yesterday. And VCE sat is approximately constant for a constant value of HFE. Actually depends on IC as well. And HFE depends on IC as well. So everything depends on everything else. It's a bit of a mess. But we can just take a value and run with it. And the value of HFE depends on the particular transistor. So we can, the E, the VCE, the E should be subscripted. Sorry about that. As it is in the line above actually. So IC on is Vs minus VC sat upon RL. So all we've done there is applied Ohm's law to the load resistor, just the same as we did for the FET. And for the same situation as the field effect transistor, IC off is 0 because the leakage is so small we'll ignore it. In the sort of CMOS 1.3 volt multi-core, multi-gigahertz processor, the leakage is actually quite significant. Now you say, alright, I've got a picoamp and 100 billion transistors. Well, that means you could have a leakage current of almost an amp across all those transistors. So even though the leakage current is small when you worry about one transistor, if you're in some VLSI problem, you could have quite a big leakage current. So to be sure that the bipolar junction transistor is fully switched on, the designer must ensure there is sufficient base current available. So you're going to provide VBE, and you've got to make sure that whatever you're using to provide VBE, so it could be a voltage source, is capable of supplying sufficient current. If it isn't, you won't be able to get big enough VBE to turn on the transistor, or you might turn it on a little bit, and if you do that, it could dissipate an awful lot of power. So you've got to make sure there's enough current available. And the base current is determined by IC is IB is IC upon HFE. So we've got a value for IC from equation 5, and then we can sub it into equation 6 and find out what the IB is that we need to supply. So the actual design process, first of all, estimate IC. So you can say it's approximately Vs upon RL if Vs is much, much bigger than VCE sat. I would much prefer to say Vs minus VCE sat upon RL because it's more accurate. And then you'd require, you calculate the minimum base current. So you'd say IB is IB upon HFE, which is Vs upon HFE times RL if you're subbing in from 7. And we know that IB is controlled by VI and VBE because if we apply Ohm's law to RB, we'll do VI minus VBE divided by RB gives us the current IB. This is just Ohm's law. Where VI is the input voltage and VB is the voltage associated with the forward bias base emitter junction, which is usually 0.7 volts. And usually it's necessary to make the available IB several times the minimum. So if I worked out for some situation that I needed 118.5 kiloohms as my maximum value for RB, I'd probably just go, I'll make it 50k. Because that's definitely small enough. Of course, on an exam paper, you would write the exact answer. Today we discussed an ideal switch and considered the non-idealities of a switch. We looked at 3 classes of switch. That's to say the electromechanical switch, the mechanical switch and the electronic switch. And we considered how the switching action of the transistor is represented on the output characteristics. We introduced the idea of a load line. If you're feeling unhappy about load lines and you weren't very happy about the bipolar junction transistor experiment, it would be a good idea to do a bit of reading about load lines because all of analog really relies on them. You never ever use them in a calculation, hardly, very infrequently. But if the concept is not one you're happy with, it will always come back to get you. And we considered power dissipation in the on state for a bipolar junction transistor and for a MOSFET. And I provided some design equations for the MOS and the bipolar junction transistor switches. So next Monday we will be doing a problem sheet style example for the transistor switch, and we'll go over some methods of using electronic switches with AC and for switching inductive loads. So you don't have to start this tutorial sheet till next week if you don't want to, but if you're feeling really keen, I promise I won't stop you. There is my mate.
Where's the book?